Okay, I think we'll make a start here, and I'll give it a gentle introduction. These online meetings always need a few minutes for people to trickle in. But welcome for those of you who've already made it. My name's Andy London, and I work at the UK Atomic Energy Authority, based at the Culham Centre for Fusion Energy. I'm an experimental materials scientist, and I work specifically in the materials research facility at Culham. And I'm going to talk to you a bit about some sort of the fundamental aspects of irradiation damage. And this is important for future fusion reactors, as well as some of the materials that we'd like to use and why those particular materials and some of the problems. I'm hoping we're going to have some good questions by the end of it. Yeah, so feel free to use the Q&A function in Zoom to ask questions, and I'll go through those at the end. But feel free to just pop anything in as you think of it as we go through. So, nuclear fusion as an energy source. The sun uses nuclear fusion to generate all of the heat and light that we get from the sun and throughout the solar system. It's primarily made of hydrogen, and that hydrogen is compressed by the gravity of the huge mass of the sun, and that causes it to heat up, and that causes nuclear fusion to happen. So on the surface, the color is actually related to the temperature, and that's about 5,000 degrees C. It's a little, depends exactly how you define the surface, but at the core, it's over 15 million degrees C as our best estimate. And that's hot enough to actually fuse different hydrogen nuclei together, and that produces fusion, and that produces a huge amount of energy. What we'd like to do is to recreate this process on Earth. So one form of fusion energy, you could say, is solar power, because the energy is coming from the fusion in the sun. However, we would like a steady baseload, highly concentrated form of nuclear power, and we can do that using fusion. So this is the Joint European Torus, known as JET, which is hosted on behalf of the European Union at the Culham Centre for Fusion Energy. And using this reactor, we can actually perform some nuclear fusion experiments. And the most fusion power that was ever produced was actually produced, or sustainable power was produced in JET in 1997. So they used two heavier isotopes of hydrogen to create fusion power. And the way this is contained, the plasma here, which creates the fusion, just like the sun is plasma, the way it's contained is in a giant magnetic vessel. So it's kind of like a magnetic bottle. We squeeze the plasma down, and we get high enough densities and temperatures in order to create fusion. Now, on Earth, we need to create a large amount of fusion power, and that means having the reaction go fast enough to create a reasonable amount of energy output. And to do that, we need to use temperatures 10 times hotter than the sun, about 150 million degrees C. Now, obviously, there are no materials that can withstand that high temperature, and that's why we use this magnetic confinement. So in the case of JET, it's a torus shape, and the magnetic field confines the plasma and traps it in place, and that prevents it from reaching the walls. And when the plasma does reach the edge of the vessel, it can have radiated a lot of heat. And that's what you can see here. So the bright spots here, this is actually where the plasma is coldest. Where the plasma is hottest, it emits no visible light. It only emits higher energies than the visible spectrum. So this is the coldest part of the reactor down here, ironically, the bit where it looks very bright and exciting. That's because we have this radiation. There are impurities that come from the wall. They cool the plasma down. And there are other strategies that we can do to cool the edge of the plasma down as much as possible before it hits the edge of the reactor. Now, the fusion reaction that's going on generates neutrons. So this is the fusion reaction of choice that we like to use. It's the sort of the easiest one to get going. That's because fusion is very difficult to actually get going and maintain. So we take these two different isotopes of hydrogen, deuterium, which has one extra neutron, and tritium, which has 2 neutrons extra. And we fuse those together at these high temperatures and pressures, and that produces helium, which is a charged particle which maintains trapped within the magnetic field. But it also produces a neutron, and this neutron carries about 80% of the energy of this, the output energy of this reaction. So the neutron is actually carrying a substantial amount of the energy. And that is good because the neutron can leave the plasma. It can heat up the surrounding vessel. So we have what we call a blanket. So the reactor is wrapped in a nice cuddly blanket, and that gets hot. And we can turn that heat into electricity. So we can, say, drive a steam turbine. And this we can use to generate electricity. So it's good that the neutron carries that energy out of the reactor. The helium, which is a sort of waste product that's produced in the reactor, and that goes back into the fusion reaction, and that helps keep the plasma hot. And eventually it's exhausted and pumped away, and the other fuels are recycled. However, this neutron, or these neutrons, which are produced by the fusion reaction, go on to damage the reactor walls. So this is a little bit like a high energy bullet that's going out and hitting on materials. So part of that energy is going to heat the materials up, but part of it causes damage. And there's something else that can happen with neutrons. These are kind of subatomic particles, and therefore they can interact with atoms and they can be absorbed. And this produces radioactivity, and it can also change the alloy composition. So there's we already have a very good webinar by Chantal talking about neutrons. So I'd recommend you go and look at that, especially if you are interested in the sort of metrology of neutrons and measuring things. Chantal also does a good job talking about some of the issues surrounding neutrons, especially transmutation. So that's this absorption of neutrons that can cause radioactivity. I'm going to touch on it briefly, but I'm mostly focusing on the damage aspect here. So when a neutron comes into a material, our materials are predominantly made of crystals, unless you have a glass. And this is a kind of a schematic of our nice ordered crystal array. And this is our nice alloy that we've worked on and made and created. And when a neutron comes in, it can displace an atom. And this leaves behind a vacant site where that atom was, and we've squashed in an extra atom. So we've got a hole and we've got an extra atom. Now, depending on how close these two defects are, they could just come back together and then they would disappear. And then we would be left with a perfect crystal lattice. But what can happen is that the atom which is displaced is far enough away that these two defects now in our crystal, our imperfect crystal, can remain. And it's often a lot more complicated. We don't usually just get a single vacancy and a single extra atom. So this is we call this a vacant site, a vacancy, and an extra atom, an interstitial atom, because it sits in between the different atoms. We call this an interstitial atom. And we often represent them like this. We only show in a diagram where the defects occur, because if you imagine all of the atoms in a crystal, and that's on the order of 10 to the 20, whatever it is, depending on how much material you've got, it's very hard to see things. So we like to just show the bits which are damaged. And what can happen in this displacement process is this atom which is displaced can actually go on to knock another atom and another atom. And it's a bit like a snooker break where you hit the balls and they break and they go all over the table, and it makes a big mess. And so we can simulate that in a computer, and that's what's going on here, courtesy of the University of Michigan. What's happening here is that there's an impact coming in from the left-hand side, and that is then causing this kind of branched, what we call cascade of damage. So one atom hitting another, causing a kind of knock-on reaction that displaces a huge number of atoms at its peak. And then as this kind of cools down, it's a little bit, you've input a huge amount of energy into the crystal. And this energy gets dissipated as heat. And in a local area, you can have what we call a thermal spike, like a local, almost molten volume where you have a really high energy. And what gets left behind are these missing atoms, so in blue. And these we tend to get at the core of these displacements, these displacement cascades. And we've got these pink or red atoms as well. And these are where we're showing the extra atoms which are left behind. And then also, quite interestingly, these defects don't like to stay isolated. They tend to cluster together and they group together. And that's what these different colored wiggly lines are. These show extra sort of little little pieces where you have a whole extra section of crystal which has been inserted, squeezed in somewhere where it shouldn't be. Or maybe you have a whole section where you've got some missing atoms as well. And it's a little bit abstract looking at something like this. And so a practical that I find very interesting and helpful is to actually try and make a 2D sort of crystal-like lattice. And we can do this with bubbles. So you can try this at home, and all you need is some soapy water and a very thin tube or a needle, a hollow needle that you can blow through. And it helps if you have a small air pump to do this, so the flow is really constant. So that the flow rate and the depth that you put this under the water affects how big your bubbles are. And for this to work really nicely, you really want bubbles that are all really kind of the same size. That's when it looks best. And this is a photograph of the top of one of these bubble rafts. So these are not atoms. These are much bigger than atoms. These are the bubbles, and we can see within this bubble raft there are some defects, things that aren't correct. So here we have this sort of extra bubble in the middle squeezed in. Maybe we have here one bubble which is slightly smaller than the others, and this is a bit like if you've got steel. Steel is made of iron and carbon is a lot smaller than iron, and so it sits in between the atoms. If you have something like maybe copper, maybe that's smaller, and so you get these sort of substitutional defects where you've got an extra thing in there which is a slightly different size. And we can have these vacant sites as well where a bubble is missing. And there's this other curious defect which is quite tricky to see, but the lines, if you follow the lines of these bubbles, you see here we've got one whole line and then another whole line, and here we've got a kind of an extra half plane of bubbles, but it then stops. And we call this a dislocation. And dislocations are hugely important in metals and in some other materials as well, because these are how a material can deform permanently. So we call that plastic deformation, where you deform something and it doesn't go back to how it was. Think of a paperclip. When you bend a paperclip, to some extent, it bends a little bit and then it springs back. But if you keep bending it, it stays there permanently. And that's because you've moved millions and billions of these dislocations, and they've caused damage to the material. They've caused this plastic deformation. So we can see this in a video. If you take your bubble lattice and you move one of the sides backwards and forwards, you can actually see these dislocations kind of popping in and zipping around inside your bubble lattice. And this is very, very similar to the process that happens within a real crystal on the atomic scale. So obviously this is just two-dimensional, so it's not entirely correct. In 3D, these dislocations tend to extend sort of out of your screen. So you have a line basically of these extra atoms. And kind of to prove a point, this is a molecular dynamics simulation. So this is a kind of atomic level simulation where each of these little blobs is an atom, and we have a model of how those atoms are attracted to one another. So we have the sort of the bonding of the material embedded in this model, and we can track the position and the velocity, so how much these atoms are jiggling around, and then we can do something to this model. So here we're applying a strain at a fixed rate, so we're pulling on this, right? That's what that means. We're pulling on our sample, and we can watch what happens. And if you look very closely in the middle, you will see, exactly as we did in the bubble raft, these little kind of defects popping in and zipping across. So initially, we have this elastic deformation, so that's deformation which is reversible, and then we start getting these dislocations zipping through. And if you did this is very, very small, so maybe there's only a dozen atoms across here, so this is really, really tiny if this was a real sized material. But you can actually take a very thin piece of wire and you can deform it like this in an electron microscope, where we can't quite see the atoms, but we can see what's going on at the very small scale. And this is almost exactly what it looks like. Here we have the stress, so this is the force divided by the area on the top and the bottom, and how much the sample is deformed, so how many times longer it's got. And we can see initially we just have this sort of straight response. If we stopped here, it would go back to where it was. But if we keep going, we get these dislocations move across. They permanently deform the shape of our sample. And you can also see that the stress here is dropping off. That's because the area which is being deformed here is actually getting smaller. So it's actually, as the material is deformed, it gets easier to deform. Now, in reality, our materials are more complicated than this, and they are larger. And that means that actually these dislocations, I'll just play it again for you. These dislocations that are zipping through, they can actually get tied up and tangled in each other. And that makes the material stronger. So actually, in most engineering steels, as we deform a material, it actually gets stronger, and that we call that work hardening. So as you work the material, it gets harder. And to get rid of that, we have to heat the material up to kind of get rid of some of those dislocations and that mess. Now, hopefully you're now thinking, well, what happens when a dislocation interacts with some of that debris that we had left over from our neutron damage? So this is the same sort of visualization, and here the lines of these defects, these dislocation lines, are colored in. So you can see in 3D exactly what these lines look like. And we often like to use a higher level of materials modeling where we don't consider every individual atom, but we only consider these line defects moving through the material. And that makes our simulations a lot quicker, and we can look at much larger volumes over longer timescales, because we don't have to track where every individual atom is, only where these lines of defects are. And then we want to see how those interact with our neutron damage. So this is our kind of debris, which is left over after our neutron impact. And of course, over time, the more neutrons you have, the more of this damage can accumulate. And that can be very bad for our materials properties. So this is what it looks like in an electron microscope. So we can actually visualize this is kind of the deformation of our crystal and these clusters which have formed. We can't see the individual atomic defects in this case, but we can see the collections of those defects. And the irradiation damage can produce these lines these line defects. These are dislocation lines, just like we had before. So the irradiation damage itself can create these dislocation lines. We can get loops of dislocation. So a defect line which actually links back on itself to create a loop. And then there's obviously other small clusters here which we can't identify actually very easily with our electron microscope. So we can create a huge amount of mess, basically. Our perfect crystal has been totally messed up. A lot of it is still the same as it was, but we've now got this huge amount of stuff, basically, that wasn't there before, and that will disrupt our dislocations. Now, this is, again, another atomic scale simulation showing a dislocation. In this case, it's a screw dislocation as opposed to an edge dislocation, but a dislocation, like I said before, one of these line defects. And there's a small stress applied, and that's driving the dislocation to pass through the crystal. Now, until it reaches these two blue voids, these are basically holes or bubbles in our crystal, it moves fairly quickly. But when it reaches these voids, it gets stuck. And that's because the atoms on the surface have to either rearrange, or the dislocation itself has to move over or across these holes, basically, in our material. And that takes more time, or it takes more force. And so what that is doing is it's actually making a barrier. It's making it harder for the dislocations to pass through the material. So like I was saying before about the work hardening, the irradiation damage also produces a similar effect. And that's a common observation, especially when we irradiate a material with neutrons, especially at lower temperatures. The material itself gets a lot harder and stronger. And you might think that that's a good thing, but I'll show how that can be actually quite bad. Let's see how it affects a material like tungsten. So tungsten is used in this lower part of our fusion reactor. So this is, again, a picture from the Joint European Torus. And it's a very high melting point material. So it's got a melting point of over 3,400 degrees C, only bested by carbon. And because tungsten is a very heavy element, it's very hard for the ions in the plasma to displace it, to knock it away and sputter into the plasma. So that's why tungsten is chosen here. It's also very good at not absorbing the hydrogen, the deuterium and the tritium that's in our fuel. Unlike carbon, carbon loves hydrogen, and carbon and hydrogen makes oils, and that's really bad news. We don't want oil in our fusion reactor. So tungsten is an excellent material for this, mostly because of its high melting temperature and the lack of erosion. But what can happen is the secondary effect, that I said about absorbing the damage, so as well absorbing the neutron, so as well as the damage in our material, and in this case you can see in these pictures here, these dark areas are actually holes. So these are those cavities or bubbles that I mentioned previously. We can actually use this is a very specialist microscope called an atom probe, which can map the chemical compositions, the ionic, the isotopic identities of the atoms in 3 dimensions on the nanoscale. And here we can see rhenium and osmium. Now, rhenium and osmium, they weren't there in this material to begin with, but tungsten has captured neutrons and then transformed from tungsten into rhenium and osmium by radioactive decay. And in tungsten, it seems that rhenium and osmium can cluster together. And they can actually decorate in this bottom right image here. There's a hole and it's got some extra rhenium around it and some osmium maybe on one side of it. There's maybe even a rhenium precipitate or a cluster shown here at the bottom. And we can see these both in the atom probe and with an electron microscope. And these are also very bad for our material. These create barriers for those dislocations and they make it harder, but also more brittle. So this is a bend test. So you take a matchstick sized piece of tungsten, and in this case it's been irradiated, and it has a very small crack put in it just at the very top. And then we bend that specimen, just like if you were going to try and snap a pencil. And we use instruments to test how strong, how much force is required to break that specimen. And we can also look at the surface where it has snapped to see how much of it has deformed. Now, in this case, these are the same material, but deformed at high and low temperature. And in this case, it is both neutron irradiated. But the neutron irradiation makes our material easier to break, so more brittle. And it also makes that happen at lower temperatures. So if you imagine in a fusion reactor, it might be very hot when it's operating, and the tungsten on the surface, maybe it's at 800 or 1000 degrees. But when we switch off the fusion reactor, it cools down. And then when the tungsten cools down, maybe then it becomes easier to fracture. And if you imagine having to replace a component, if it breaks, then that's really bad news. So we need to really know exactly what's happening in our material, and to be able to monitor these changes and to predict the life, especially to figure out how much more brittle and how easier it is for these components to break. And this is we call this the fracture surface. So this is what's left behind after it's been broken. In this case, you can see there's lots of features here. There's lots of bits of the sample which are kind of sticking out, and this shows us this quite a lot of dislocation motion. So the dislocations have moved to where the crack is, and they've helped blunt it, and that's soaked up more energy, and it's made it more difficult to break, and it's made it tougher. On the right hand side here, this is a test, I think, at room temperature, and there's very, very few features here. And if you look at this, you would be excused if you thought this was actually just a piece of glass. When you break glass, there is very, very little deformation. It just snaps kind of clean through. So, and that's exactly what's happened with this tungsten. It's almost entirely brittle, just like glass. And this is what we want to avoid happening to our materials, because we don't want to build our fusion reactor out of a material which is basically the same as glass. We can do these very same sort of bend tests on the micrometer scale. So this is a pentagonal cross-section cantilever, which we've sort of shown at a 3/4 view. So this is it's in 3D, it's free underneath. We can use a piece of equipment. We have one of these at Culham, for example, called a focused ion beam milling machine. And using this equipment, we can actually cut out very, very small pieces of material. So to give you an idea, this cantilever is so small that if we wanted, we could place 10 of them across the diameter of a human hair. So if you imagine doing your tests on your materials, you've got a matchstick of material, or you've got something, say, the size of a human hair. Now, if we're talking about materials which are potentially radioactive or very expensive, it makes sense to use a small amount of material as possible. And so using these cantilevers, we can actually do these tests on a really, really miniature scale. And that's kind of one of the main areas that I'm looking at. And that's why I've included it here. Anyway, we can do these same kind of bend tests where we use a manipulator to press on the very end of our cantilever, measure how much force is required to deform it, measure how much it deforms, and we can also cause cracks. So here again, we've got this brittle fracture, which has happened at the base of this cantilever as a result of the neutron irradiation that it was subjected to. So we can do these kind of tests at very small scale. Now, something we can do about this, so this is one of the ways we can mitigate this problem, is actually by making a fiber composite. So if you take a big piece of copper, for example, it's quite strong and it's not very bendy. If you take a copper wire, which is in, when you plug your phone into charge, you're deforming a piece of copper wire, but it doesn't permanently bend and it doesn't instantly snap. And that's because it's a very, very thin fiber. And when you make things smaller, our observation is that they get sort of stronger. And we can use that to our advantage. And as the crack, so this kind of wedge shape here, this is a crack trying to propagate through a material. As these fibers get pulled on, their fibers can deform, they can kind of come away from the surrounding material, and that makes the material a lot tougher. And for example, this is some real tungsten composites of different kind of lays up, different amounts of fiber and so on. This is pure tungsten down here. So this is how much force or stress we're applying, and this is how much it's deformed. You see the pure tungsten is down here, but the fiber composites behave much more ductilely and also stronger. So they're stronger and they're much more ductile. And this holds up as well when we neutron irradiate these specimens as well. So using fibers is one way. It's kind of like materials engineering. Normally materials engineering involves, say, changing the composition or the way a material is processed. In this case, we're kind of changing them sort of mesostructure. We're changing the design, like the design of the component, and changing the engineering of it in order to make it tougher and change its response. Another example is looking at advanced steels. This is a prototype blanket module for ITER, so the next generation of fusion reactor, which is being built in the south of France, and is, as I think as of yesterday, 70% complete towards their first plasma. So when I started my research into fusion materials, they were just laying the very first foundations, and now they're 70% of the way to having their first plasma in the device. So it's very exciting. This is made out of stainless steel in this case, and steel is great because steel is widely available. It's a well understood material. It's fairly cheap. And so it's an ideal candidate for building our fusion reactor out of. It's also pretty good at not absorbing too many neutrons and causing any kind of radioactive waste. So our estimate of the if you have just what we call a ferritic steel, so that's without nickel, if we irradiate that in a fusion reactor after 100 years, then we would be able to recycle that fairly easily. So iron on its own is a really good element for use in a fusion reactor, and it's not giving us that really long-lived radioactive waste that you get from a fission reactor, for example. Anyway, so steel is strong and tough, and we can improve it by adding nanoparticles, and I'll explain why we do that. If we just compare our material before and after irradiation, these extra barriers, like I said before, they cause the material to get stronger, but also less ductile, so more brittle. And what that means is it's going to be harder to deform initially, and then it's going to break. So the unirradiated material, maybe the stress strain curve looks like this. So when we pull on it, you get this elastic response here, where if you let go of it, it just springs back. If we keep going, we get this plastic deformation, and it sort of gets a little bit stronger. As we increase the amount of irradiation here, then it's getting stronger and it's getting more brittle. Okay, so how can we limit that? Well, again, this is sort of like making a composite. We can introduce these really small particles, and this is work done as part of Eurofusion, developing new steels. We can introduce these small particles, and this is just by changing the processing, so the composition of the alloy and how it is heat treated, to produce these really, really tiny nanoscale precipitates. And there are other ways of doing this as well, but the effect that these precipitates have is that when you get one of those cascades of damage, in an area where there are no particles, you end up with this debris left behind. But in a place where you have one of some kind of particle, some sort of interface, then the damage can collect on that interface, and then it's not as bad as it would be if there was no particle there. So introducing these particles is a way of reducing the amount of damage which accumulates in a material. But then we have a question about how resistant these particular particles are, and there's different materials we can use, and they have different advantages and disadvantages. But this is one of the ways that we're developing advanced materials which can have a longer lifetime in a fusion reactor. So just to give you a kind of materials summary, it's all about making materials like we saw there, making a new material or changing the structure. We want to characterize where the atoms are, what they're made of, whether we're forming precipitates. This gives us certain properties of our material, and that leads to a certain performance. So how hot we can operate our fusion reactor, or for how long we might be able to use it in a safe manner. And this bringing this all together in a particular steel, we maybe, if it's powder processed, we look at how we make the powders and how they combine together to give some sort of structure, and we can measure the properties, and then we want to design and engineer our actual fusion reactor at the end of the day. So that's a very brief overview of some materials and damage, and I hope that we've got some interesting questions to answer. I'm going to be sticking around until probably until about 2:30 to answer some questions. And with that, thank you very much. I will now have a look at the questions. So hopefully you can still see my screen with the questions open. So first general question about nuclear fusion. What's the outlook for nuclear fusion? Are we likely to see commercial use in the next 20 years? So there's kind of a number of different ways of answering that. I think in 20 years' time, it would be highly optimistic to have electricity coming out of your wall, which was produced by fusion. However, there are a number of research programs, as well as private companies, all set with their sights firmly on producing fusion. So in the last 10 years, there's been a huge ramp up in the amount of money which is being spent on producing sort of viable fusion power. So, for example, at UKAEA, we have a project called STEP, which is looking at using small spherical reactors in order to produce electricity. And our aim there is actually to put electricity on the grid. So with ITER being built in the south of France, that will demonstrate the technology required to generate electricity, but it will not generate any electricity. It is only designed as a fusion experiment. And they are looking at their, I think, first plasma in something like 2025, and then we've also got probably using actual fusion fuel and generating a lot of power maybe by 2035. So that's well within the next 20 years. But in terms of hooking that up to the grid, that's not in their sights. But for STEP, that's something that we're aiming to do, and that's hopefully going to be sort of on that timescale in the next 20 years, I think. I have another question here about boron. Could we use boron as a material because it has a high melting point and boron carbides are very hard? Yes, boron is a pretty attractive material in that case, and boron carbides are extremely hard, harder than diamond in some cases. There is a nasty effect of boron, though, is that it loves to soak up neutrons. So boron is used in fission reactors to soak up the neutrons, especially in the case of an emergency. If you need to get rid of all the neutrons, you dump a bunch of boron in the reactor, basically. So from a neutronics perspective, boron is probably out as far as a fusion reactor is concerned. That said, I think there are certain steels and alloys which do include boron. Specific nickel alloys, for example, is an excellent alloying addition. What kind of loads do the blanket tiles face? Are they structural elements? So that's a good question. It depends. Obviously, it depends on the design of your reactor. And for something like ITER, those designs are set, but for the sort of next generation beyond ITER, so the demonstration, the demo reactor that we talk about after that, always something like STEP, we're still trying to design our reactor. Basically, we're still trying to figure out exactly what sort of engineering loads that they would be subjected to and whether they are structural elements. Certainly some part of them has to be, they are in a sense safety critical components because they contain coolant. So that's how we get the energy out of a reactor, by circulating coolant and that heating up. So in that way, they are quite important and structural. However, they also I think would sit inside the vacuum vessel. So if your blanket failed for whatever reason, maybe you develop a crack, that means you don't get air. In this case, we're not worried at all about the fusion reaction escaping, because that would instantly stop if there was any kind of accident. But we're worried about air getting into the reactor, or the possibility of something inside the reactors, maybe some material, whatever, from being vented to the atmosphere. And so they would be, I think, inside the vacuum vessel. So from that sort of safety perspective, there's less of a problem. So the question is, does this also adversely affect the heat transfer capabilities? I'm assuming we're talking here about the irradiation damage, and the answer there is yes. So with tungsten, for example, it can cut the thermal conductivity in half. So it makes them much worse at conducting heat. And that is a problem for the diverter region, for example, because we have to conduct the heat out of our diverter in order to prevent the surface from melting. So one of the approaches here to mitigate that problem is actually to have some kind of in-service annealing. So there's this kind of nice property of materials that as they get hotter, then the atoms move around more, and this irradiation damage actually kind of self-heals itself. So with the very front-facing material, it's probably going to be hot enough that it's not going to be accumulating enough damage to really to damage the thermal conductive properties. But we could also look at actually annealing the material in situ, maybe using some sort of laser pulse or some heating arrangement to actually get rid of some of that damage and recover the properties. And so that's one of the sort of technological things that we have to consider with how we're going to operate our reactor and make sure that it lasts for a long time. We have a question. Thanks for the talk. Are the slides publicly available? Will there be a recording of this? If you contact the communications email, I'm sure we could get you a copy of the slides. Can you discuss other candidate materials for any/all of the diverter, plasma-facing components, and vacuum vessel? I don't think we have quite enough time to discuss all of the different materials. I did only focus on tungsten and steel. In terms of the diverter, tungsten is our kind of key material because it has such a high melting point. Tungsten composites is another important one. There we're mostly looking at tungsten alloys, so adding small additions to our tungsten to improve its properties and to make it oxidation resistant, so to prevent any kind of oxidation if there was air ingress into our reactor when it was hot. That's quite important from a safety point of view. In the diverter, there's also a lot of other materials. So tungsten, we wouldn't be using as a structural component, and it wouldn't be used for the coolant pipes, for example. For that, we would probably use a copper alloy, so copper, chrome, zirconium, for example. We'd also probably have steel, and I imagine ferritic steel for the structure in the diverter. For the plasma-facing components, we like to use, historically we used carbon, because carbon is a very, as far as the fusion reactor is concerned, it's a very friendly material if you were just building your very first fusion reactor, because carbon has this nice property that it doesn't melt, but it will sublime at high temperature. So instead of creating molten droplets or breaking off small pieces, it just evaporates. And because carbon is such a light element, that means it's only got 6 electrons for every carbon atom. You don't get a lot of contamination in your plasma. So the more electrons you have in your atom, the more potential there is to poison your plasma effectively. So JET, for example, was first built with an all carbon wall. The whole vessel inside was all made out of carbon. And that was this kind of convenience factor. But like I said, when you introduce hydrogen, then carbon and hydrogen love to bond together, and the carbon absorbs all of the hydrogen. And with a real fusion reactor, especially where we want to use tritium, and with the supply of tritium at the moment being quite limited, then soaking up all of your tritium into the carbon wall is a really bad idea. So that doesn't totally rule out carbon composites it doesn't mean that we can't put them at all anywhere in our reactor, but they would definitely be really limited. The other material is beryllium. So this is a metal, so it melts when it gets really hot, but it's also very light. So it's friendly from a plasma physics point of view. And at the moment, the main challenge is actually getting the fusion reaction going and keeping it going. And in that case, we want to avoid, the heavy elements as much as possible. Tungsten is okay because it's heavier, which is bad from a poisoning point of view, but because it's so much more difficult to sort of sputter off the surface and get into the plasma, then that's less of an issue. So in terms of your plasma-facing components, tungsten, carbon, and beryllium are your main candidates. For something like at the blanket level, it would probably be a thin layer of tungsten and then a backing of steel or some advanced steel alloy. In my previous research, I looked at oxide dispersion strengthened steels. So these are alloys with very small oxide particles inside, and these are very, very strong and tough and very radiation resistant. In the blanket itself, then yes, it would probably also similarly be some sort of steel alloy. People have looked into using some more exotic things like vanadium or maybe molybdenum. But again, there's also, you have to do a kind of cost benefit availability sort of analysis, and that's tricky. The vacuum vessel is less of an issue from a radiation point of view, although in a kind of real commercial reactor, it would almost certainly accumulate some level of damage. There we can use much more conventional materials. JET, for example, is made out of a nickel alloy, out of Inconel, and that's very strong and heat resistant. ITER, for example, is made out of stainless steel. They're using superconducting magnets, so you have to worry about the cryostat. So you have to have cryogenic liquid and coolant going around. You're getting, the further away you get from the edge of the plasma, the less of an issue your neutron damage tends to be. And you tend to also, then you get other engineering or technical challenges which become important. But probably stainless steel for the vacuum vessel, maybe nickel in a pinch. Steel is really attractive because we just produce so much of it and it's so cheap and readily available. Let me just have some tea. Does UKAEA also work on reactor cooling concepts for the first world diverter? There was actually some, I don't know a huge amount about this, but there was a news article recently about using sort of heat pipes, which is a technology I'm familiar with from cooling computer chips. There's also, we also do some work on sort of concept designs, and this is less on the sort of practical side, but more on the kind of computing side and simulation. What would it mean if we used a liquid wall, or what would it mean if we used some other kind of fancy technology, and how would that affect the kind of overall balance of plant and things like that? So yes, I think we don't work so much on the practical side of that, but more on the kind of conceptual side of that. Hopefully that answers your question. I have a question here about the lithium. How much protection to make the lithium blanket of the steel wall? So lithium is an interesting one because something I didn't touch on is that to produce the tritium, we use a neutron multiplier, which is beryllium. So this is inside the blanket. So inside, it's a big complicated component. Inside that, we breed more neutrons using the beryllium, and then the lithium is used to produce the tritium. So there's not very much tritium available because it's a radioactive isotope. It has a half-life of about 12 years. So there's no naturally occurring tritium. We have to get it from existing fission reactors. And a fusion reactor would have to breed its own tritium, produce its own tritium fuel. Now, we don't need a huge amount of tritium or lithium to make our fusion reaction work. That's the nice thing about fusion, is that it uses relatively abundant fuels. But we do need to produce this tritium, and there's a whole tritium fuel cycle, and that's probably a whole webinar all to itself. In terms of protection and the steel walls, we are trying to make, we're trying to focus on these alloys where we have some amount of irradiation resistance, and it does depend very much on temperature, so it's a little tricky, but it's all about this kind of combining the structure and the material and the design in order to make a component which has a reasonable lifetime, which can be replaced and recycled. And so there's not really a sort of an easy way of boiling that down into a protection factor or amount. The damage of a material is usually measured in this thing we call displacements per atom. So if you have 100 atoms and one of them is displaced, then we would say that's 100th of a displacement per atom. So in that case, where you have the cascade, you have that big kind of explosion of damage inside your material on the atomic scale. We might talk about creating like locally, like one displacement for every atom in that volume. We talk about end of life doses of something like 10 or 50 displacements per atom. So that means, in terms of the energy deposited, there's been enough energy to displace every atom in your material 10 times or 50 times over, which, when you think about the atoms being jostled about, sounds like a lot. But it's very much about the kind of the engineering and the technology to make those levels of damage bearable in the best way possible. There's a general question here. Which UK universities offer undergraduate material science degrees that would be best suited to a career in material science for fusion research? So I would say at the undergraduate level, any kind of first of all, any kind of physics degree would give you an excellent grounding. The same for a lot of engineering degrees. There are universities which offer specific material science options. So Oxford, Cambridge, Manchester, Birmingham, I think Surrey, Bristol, they have very active, Sheffield and Leicester, I think as well, they have very active material science research groups, even sometimes if it's not exactly called material science. Any of those would give you an excellent grounding. There is at the moment a fusion CDT, so this is a doctoral training center. So for then at the PhD level, that's where you can really get into something which is fusion specific. I know Birmingham offer a nuclear materials course, and that's also an excellent basis for getting into something fusion related. So fission and fusion, more or less interchangeable at the sort of science level, and so any of those would be great. Hopefully that's enough to answer your question. We've just got 2 more questions. I think that's going to be it. One of them is a comment. The tritium is from the Canadian CANDU reactors. Yes, so those are heavy water-fueled reactors in Canada, and they produce tritium as a byproduct. And tritium is not just used in fusion, it's used in a number of different applications in physics and even medical cases as well. So that's the main kind of market for tritium at the moment. At CCFE, what are the aims of the MAST-U project? Are scientists hoping to translate from MAST to STEP? So again, this is kind of a CCFE. It's not really materials. There are some pretty important materials involved in the MAST-U project. Again, it's mostly carbon walls because we're focused on the plasma physics. MAST stands for the mega amp spherical tokamak, and the U stands for the upgrade. So this is an upgrade to the original MAST device, which we have at Culham. So another tokamak, another spherical tokamak that we have at Culham. It's recently been upgraded and improved. Again, there may well be a webinar about MAST. I'm not entirely sure about that. If there's not, maybe there should be. The main thing there, the main objectives they have there are about operating spherical tokamaks and improving their diverter, and those are things which are really relevant to STEP, so the spherical tokamaks for energy production. I think we are expecting we'll be able to use a lot of our knowledge, a lot of our knowledge on operating MAST in terms of the design and the operation of STEP. So we are, kind of world-leading experts in spherical tokamaks from MAST, and we're hopefully going to translate that into STEP. Apparently, Nick has a video on MAST on our YouTube channel, so check that out. And the YouTube channel is also where you'll be able to find a recording of this webinar. And with that, I think we're pretty much all done. So thank you very much for listening. Thank you to those of you who stayed all the way to the end. I hope you've found that interesting and exciting. Thank you very much.